I hope now I am audible. I have changed the mic also. Ah, fine. Okay, so from this one, it seems that you couldn't hear me. So for this question, what we are saying that this is a system GS, like open loop system, and the compensator system that if we have this feedback closed loop system and we have a compensator GC with the system GS, then these following specification are made. So this MP, which is a peak overshoot and settling time, these two corresponds to transient response, and KV, which is a velocity error offset, it corresponds to this steady state response. So these response are made. Basically, this is what being said. Now, when we are saying, so the question is, if only gain adjustment achieves the desired response performance, what is the value of gain? So what is the objective to achieve the transient performance? So in that case, you have gone through the lectures and you have seen that, okay, for improving the transient response, we have different steps that we follow. So first we have that we try to increase the gain, and we say if the specified with the specification which leads to some dominant pole is lying on the root locus or not. And if it is lying, then we say, okay, if we increase the gain, we can achieve that transient response. If it doesn't lie on that root locus, then what we do, we just include this lead compensator so as to improve the transient performance. So for this system, we have seen that if we see the peak overshoot and this, we find that this zeta is 0.5, and from this TS, which is a settling time, we get omega n is 2 radian per second. So if we have zeta and omega n, so we can find this dominant closed loop pulse, which is this one, and this is -1 plus minus j root 3. So now we have to verify whether this lie on the root locus or not if the gain is increased. So if we see the root locus, this is the root locus, we have two poles, 0, -2, and as the gain is increased, so at gain equal to 0, the poles are at this. So this is open loop system, and with gain tending to infinity, this root locus looks like this. So pole moves like this. So we can see this point is -1 on the real axis. So -1 is there. Now this j root 3. So as gain is increased, it covers all the imaginary value. That means this lies on the root locus. And this we had seen from the root locus plot of from the MATLAB also. Okay, so we have gone through the lectures where you saw that how to draw the root locus of a system. So we have this fifth, which is 1 by s squared plus 2s, which is a system. And then we draw the root locus for this one, which is r locus 6. And this is the plot that we got. This is -1, and we had said that, okay, we want -1 plus minus j root 3. So for going to that limit, I just change the limit. It will be suppose. Okay. So just get a data strip here. This is the pole. The gain is 1.96 and pole is -1 plus 0.98. However, we want root 3i. So root 3 means 1.73 something. So we'll just increase this gain, and if we see here, we get 7.3. So -1 plus 1.73 I. This root we get at gain 4. Now we'll just see that whether from theory also we get this. So since the root lie on the root locus, what is said that this would satisfy this? magnitude criteria, because what is the root locus? It's just a movement of roots, closed loop poles, and that satisfy the criteria that angle of G should be minus 180 degree, 2n plus 1, 180 degree, and this magnitude should be 1. So this was the overall thing. If this is unity feedback, if this is with different feedback, so there will be a feedback transfer function which is h, so this will be multiplied. Okay, so this is a magnitude criteria that has to be satisfied. Now, if we say that at this pole it is satisfied, so we'll just have this one, and k will be equal to magnitude of st plus 2. So st is minus 1 plus j root 3, and this magnitude will get 1 square plus root 3 square by root over. So this will be root 4, and st plus 2 will be minus 1 plus root 3j plus 2. So this will be again be 1 plus root 3j. Earlier it was minus 1 plus same magnitude. So we'll get k equal to 4. So that means at k, that is gain is equal to 4, we get this transient response, and we said that okay, we'll try to verify this. At least if we can't verify peak overshoot, we can verify this. Okay, peak overshoot also we can verify. This is 16.3%, no? So it will be approximately 0.163. So it's 1 plus 0.163. So 1.163. So we'll just apply the step input to the closed loop system. Now, because this is the overall specification of closed loop system, so for that we form a closed loop system which is feedback. We just use this command feedback. We have this open loop system, which is this one, this that we have included, and we have found out gain which is equal to 4. So we have multiplied system by gain, and the feedback gain is 1. So this is a system which is a feedback system, like overall closed loop system transfer function. Now we'll apply the step input to this. We'll just write this command step input, step, this f. We'll see the step response. So let us see the characteristics. We'll see the settling time. And what other thing is this? We have to see the peak response. So it's approximately what? It's approximately 1.16, you can see. Overshoot 16.3%. And the settling time is approximately 4.04 seconds. So approximately equal. Okay. So this we have verified. Okay. Transient response is met by just increasing the gain. Now the another thing is this kV is equal to 20 error constant. So let us see what the second part of the question is. The velocity error constant of system that meets the desired specification. So what would be the velocity error constant for this system? So we know that for this velocity error constant, we have this formula kV equal to limit s tends to 0 s gs, where gs is this forward transfer function, forward loop transfer function. So now for the closed loop system, we have found the forward loop transfer function which is k equal to 4 and s plus 2. So we have transient response satisfied, and we are applying this one simply. So we have limit s tending to 0 s 4 by s plus. So this will be 4 by 2 equal to 2. So this is the value of kV, or desired kV that we can say. This is the value of this kV which is there for this improved system. So this system with improved transient response. Okay. So this is the value of kV. Now we'll proceed to next part. Now suppose we design a lag compensator, the value of beta is. So from this question, like these are all parts of same question. So we have seen that okay, transient response is met, but we have this kV which is equal to 2. But what is the specification given for kV for closed loop system? This is 20. So kV has to be increased to 20. So as we increase kV, what will be this error constant will also tends to, it will decrease with increasing kV. Okay, so this has to be increased. Basically, the steady state performance has to be improved. Okay, so this much we know. Now for improving this steady state performance, we know that we have to use this lag compensator so that transient response is not affected and we can achieve this minimum steady state error. Since this is kV, so minimum steady state error for ramp input, because this transfer function which is gs equal to 1 by s plus 2, this already has a pole at 0, or we can say has an integrator, so it will always track this step response. There will be error in tracking ramp input. Okay, so for this one, we know that for lag compensator, we add a pole and then we have a 0, and the transfer function that we have is s plus 1 by tau plus 1 by beta tau, and this beta is greater than 1. So this is 1 by tau, 1 by beta tau. Because beta is greater than 1, so 1 by beta tau will be less than 1 by tau. And this is minus in the left half. Okay. So from beta, like for beta, we saw that in the lectures that beta is equal to kV for desired one by kV of uncompensated system. Basically, for the system in which the steady state error has not been improved. So for kV desired, we have 20, and this actual kV that is for this system is 2. So that means beta should be 10. Now by choosing one location of 1, either it be 0 or it be 4, we can find the another one. So at least we know this one. So this will be 10. So now we'll try to place the pole and 0. So it is said that pole is at Gc equal to minus 0.01. So we had this transfer function Gc equal to s plus 1 by tau plus s plus 1 by beta tau, and then we can say this is Zc, and this is where beta is greater than 1. Okay, so we know Pc, and so we have to find what is the compensator 0. So what is this? This is basically minus 1 by beta tau. This is equal to, so this is minus 0.01. So what will be minus 1 by tau? This will be beta into 0.01. And beta, what we have found out, this is 10. Minus 10 into 0.01. So it's minus 0.1. If we see now we see the open loop transfer function. So we have this Dc and we have this G. And G is equal to 4 by S plus 2. And this is equal to S plus 0.1 by S plus 0.01. Okay. So in S plane, the open loop poles are at this place, then at minus 0.01, 0.1, this is at 2, like this. So we'll just draw the root locus for this system and we'll see whether the steady state error has decreased or not. We have this system. This was this. So we'll just say 6 equal to 4 into 6 because this is the overall Planck, and we have a compensator GC which is equal to transfer function 1, 0.1, and we have 1, 0.01. Okay. Now these two are in cascade, so we'll just multiply these two and we'll get the open loop transfer function. So this is 6.1. So this is 6 star GC, and we get this one. Now we have to plot the root locus. So this is the root locus of this one, and open loop force at gain k equal to 1 because we have included this is 0.0. If we see this gain we have included, so what we'll see for k equal to 1 only, we have to find what is the location of poles, and from there you can see it is very close to this 0, one of the poles. This is very close to 0. This is another pole. Let's see. This is going towards the this is going towards this. Let's see. Okay, fine. This closed loop pole that we have find earlier. So this was -1 plus √3. So at gain k equal to 1, it should be equal to that one only. See again. At gain k equal to 1, what we are supposed to find that this should be equal to this is 0.953 plus 1.17. Okay, so this is approximately equal to -1 plus √3, so which is 1.73 J. Now there is this change because we have added this 40. Now since this pole is tending towards 0, but when it tends towards 0, you see this location, when it tends towards 0, it's not totally cancelling this one, no? This pole. So there will be some effect of this one because of this. There is little change in this dominant pole, but otherwise approximately response will be same. Okay, so this we have seen from the root locus. Now I'll see that okay, this is the overall thing, and now we'll see what is the response in terms of closed loop system. We'll have this one. We have this closed loop system. So earlier when this was uncompensated, we had some error. Now we will have some other error. Now this should be decreased because kV has increased. So we'll just verify this one. Earlier we had this system, just this one, and we have this closed loop feedback with unity gain. So we said a step response of feedback with forward path shift, and this one gain Feedback of 1. So we have this response for system with improved transient response. Okay. So this is the peak response. Then we had the settling time, and we had some steady state error. Okay. Fine. We had this KV, no? So we have to see with respect to this ramp with respect to this. This is a supply ramp. So ramp, basically we have to apply ramp. Now in MATLAB we don't have this ramp input. We have this step command to find the response to a step input, but when we are saying ramp, so this is, if this is represented by 1 by s in Laplace, then this we can represent by 1 by s squared. So then if we say this s applied to 1 by s multiplied by this one, this overall system. And this will give us the ramp response. So first we have to find the overall system, which is feedback, this one. And then we have to find a step response for this one with PF 1 comma 1 by S. So S plus 0 star feedback is comma 1. Okay. This is a response. Now, if we try to find the response for compensated system, so we have this GC equal to this one and C equal to, run it again, this is GC for lag compensator, and we have this new system which is GC into this, so this is one. And then we have to find the step response with this one. Since I have some errors, I will go through Simulink then. It will be easy also. Okay, let it open. Then we'll proceed to next question by then, and then again we'll come back to this and we'll see how the response is changing. Basically, the steady state error is decreasing for this compensated system. This we know by theory, but we'll see in simulation also. Okay, so we'll proceed to next question, and the next question is that the open loop transfer function of a unity feedback system is this one. So this is GS equal to 2 by S, 2S plus 1. And we have the system with GS, unity feedback. Okay, it is designed to design a lead compensator such that closed loop system has damping ratio of 0.8 and settling time of 10 seconds. So zeta is equal to 0.10 and Ts equal to 10 seconds. So from there we can find omega n. So this will be 0.5. Okay. So if we know zeta and omega n, we can say what are the closed loop dominant poles. This will be St equal to minus theta omega n plus minus j omega n root under 1 minus theta square. So just substitute zeta and omega n, we will get minus 0.4 plus j 0.3. Okay. So these are the closed loop poles. Now it says the magnitude of angle deficiency in degree is. Okay. So we have this one. If we see the root locus plot, so we have at this point we have minus 0.5. At minus 0.5 at 0 there are two poles and the root will move like this again, where this will be minus 0.25. Okay. So this much we know that this will be minus 0.25. And the roots that are desired is minus 0.4, j 0. So it is approximately like this. Minus 0.4, something 0.3. So minus 0.2 like this. So it should be lying at this point. But if we see, so for lead like for improving the transient response, what we saw, we'll first increase the gain and say if this can be reasoned. Now, while we increase the gain, we see from k equal to 0 and k equal to tending to infinity, this like force evolve like this. So it is not passing through these poles. This root locus is not right. So this increasing gain is not sufficient. So what we need to do, we need to add a lead compensator basically. And for that, what we have to do, we first have to find what is the lead or angle lead that is required. So this angle lead will be V of S at S equal to ST. So we'll just try to find it out. This is the angle at this point. So we'll just draw this line. We will draw this line and we'll try to find this angle. Okay. So let us just simplify it, make it more clear so that we can find it. This is 0, this is 0.5, this is minus 0.4, and we have this point which should lie on the root locus. This is 0.3, this is also minus 0. This is sigma, this is 0. Now, this overall angle that has to be contributed should be minus 180 degrees so that it passes through root locus. So we just draw this line. This is the angle contributed by this pole, and this is the angle contributed by this pole. So what would be the angle? So if we find this angle, this is the perpendicular. So this will be minus 180 minus tan inverse. Now what would be this angle? Because this is total is 180, and we'll just subtract this angle. So this angle will be tan inverse this perpendicular by this base. So this perpendicular is 0.3 by 0.4. This is one angle contributed by this pole, and then there is another angle which is contributed by minus 0.5. So this will be this angle which is tan inverse this perpendicular which is 0.3 and this distance which is 0.1. Now you just simplify this or calculate this one, you'll get minus 214.69 degree. Okay, you can use MATLAB, you can apply this A10 command and solve this, or you can use calculator. So this is the angle contributed by these open loop poles. And what we want to add a lead compensator. We are just cascading a lead compensator. There will be a 0 and there will be one pole. So overall angle of this compensator system should be minus 180. So that means angle deficiency is what? Means how much angle has to be given? This is minus 214.69 plus 180 degree. So this has to be provided, and plus 180 minus 214.69 degree. So this would just give 34.69 degree. So this much stage lead has to be contributed by this lead compensator. Okay, so this we know. What is the question that is being asked? This angle deficiency. Okay, we have found it. This is 34.69 degree. Now I will proceed to next part. We will just complete this whole lead compensator design through this question. The magnitude of lead compensated pole and the magnitude of lead compensated 0. This has to be found out. So we know phi, which is 34.69 degree. And what we have to do? We have this gamma, which is the degree of freedom. We will just have this one. 180 minus theta minus phi. So we have this phi, and then for theta, we know what is the damping ratio, that is 0.8. So we can find the theta, which is cos inverse 0.8, and this would give 36.86 degree. So if you find that gamma, this will be 54.22 degree. If you substitute these two. Okay. Now simple, because we are doing this whole thing and we have to do calculation also. So just see if the lead compensator is S plus ZC by S plus ZC. So ZC will be equal to omega n sin gamma by sin gamma plus. These things we have gone through in lecture. So this will be omega n sin gamma plus theta by sin gamma plus theta plus phi, which will be equal to 0.616. So this ZC and PC we have found out, which is 0.405 and 0.616. So what was the system? There are two poles. There will be 1 0 here, 0. This will be approximately at this point, and there will be a pole at this point. So these are added. Now this root locus will change because these poles and zeros are added. So we'll see how this evolves. And if we have this, then this angle criteria is satisfied. Now we need to find what is the gain at which this desired performance. That basically this SC, which is the desired closed loop pole. That is N 0.4 plus J 0.3 is there on the root locus. So for this, we have this KC S plus 0.405, which is the compensator. So basically we have this GC and we have this G, which is here in we have S plus 0.405 by S plus 0.616 in the first one. So we'll just have Kc into this by S plus 0.5 S plus 0.616. So magnitude at S equal to St that we had found is equal to 1. We'll simplify this, we'll get Kc equal to 0.1948. Okay, so at this value, this root locus will pass through this compensated poles or this dominant pole. So now let us see how this thing we can see in the MATLAB, how we can verify. So we have this system, which is y 2s square plus s. Okay. So suppose we say that 1 by s square, 2s square plus s, and we'll try to find the root locus. So we have system which is equal to Ts 1 by 2s square plus s plus 0. So this is the system. We'll plot root locus of this system. We know this type of plot will be there. And then we had the compensated, like compensator, which is the lead compensator. So we have this GC equal to CF. There's the pole and 0. So this was 1, 0.405 by S plus 0.616. This is GC. And what is the root locus for this improved system? So we'll just hold on R locus, this GC multiplied by 6. See, this is the improved root locus, this green and red. And for this system, we say that at some value of k, this root, that is minus 0.4 J03, is passing through the root locus. So this is our improved locus. This was the earlier root locus. Okay, so value of k, what we got? That was 0.1948. That is Kc. So here there will be some gain Kc. But apart from this, we had this 2 in the plan. So overall k is, because in plotting we had not considered this 2. So overall gain is what we say, 0.1948 into 2. So this is what we are expecting. So let us see what is the value of this one. 0.1948, or we can say 5 into 2. So 0.39. So this is the value of k that we are expecting, and at this value of k we are expecting that the pole passes through minus 0.4 J 0.3. This is the value 0.39. Okay. So let us increase, it is 0.33. So 0.3. So this is approx 0.87, approximately 0.39. And at this position, the pole is, like at this gain, the pole is minus 0.401 plus 0.298. So approximately 0.4 plus 0.3i. So this is what we are getting from the root locus. So basically the response is improved. So from the closed loop system, root locus analysis, we are saying now for this gain and this adding of this lead compensator has led to the desired response, or we can say desired closed loop dominant pole. Okay, now you see if what is the step response of this system. So the earlier system was this. Okay, and we had plotted the root locus for this one. So now we'll deal in terms of actual system. So we have this equal to this one. Actual system is this equal to 2 star this. Now we have to find a step response of the closed loop system because this is a unity feedback system. So we'll have feedback this comma 1. This will give the feedback. This is the response of this closed loop system with forward transfer function or open loop transfer function GS, which is 2 by 2s squared plus s. Now what we have done, we have improved the transient response. That is, we have shifted the root locus to left that we had seen just now to the root locus plot, and we know that this from this one we'll get this damping ratio of 0.10 and settling time of approximately 10 seconds. Okay, when we are adding the lead compensator. So we'll just have the response for this closed loop compensator system. What we have GC is this one. We'll just have a new open loop system which is this 2 equal to this star GC star, the gain that we had found, which is 0.9 something, 0.1948. 0.1948. Okay, so this is the system open loop transfer function, and we'll see the step response for this one. So hold on, step feedback new system, comma unity feedback. Let us see what is the response. So this red one is the response of this compensated system. So we can see, now let us see what is the settling time. What is for this uncompensated system, that is the blue one, it's approximately 14 or 13. It's 14.1 seconds. For compensated, it's 9.98. What was expected? We expected TS to be approximately 10 seconds. No? 10 seconds. And this damping of 0.8. So damping of 0.8 basically means we have like near to this critically damped system, near to, because damping is 0.8 and we know like if damping is greater than 0.7, then there will be no peak overshoot. So we don't have any peak overshoot that we can verify from this spectrum. So I hope this question is clear. Now we'll go back to this earlier question where we had verified this. We had to verify how the steady state specification changes. So we had this system G and we had this compensator GC, which is a lag compensator. And we said that when we include this one, the error constant is increasing. We just have this Simulink plot. Let's see how. I hope you know about Simulink. It is basically a block-based simulation environment. We can have different blocks needed for this control system design purpose, control system analysis. Also, there are also different blocks also for different purposes, but we'll deal with that one. Okay, so just comment it out. We'll add a transfer function. Okay. Then one more transfer function. This is connected in cascade, and we have this comparator, which is sum with plus and minus sign to provide RAM input, and we have this feedback, which is unity feedback. Okay, now we'll change this transfer function. This is 4 by s squared plus 2s. This is the one. This 4 by s squared plus 2s plus 0. And what is the compensated transfer? S plus 0.1 by s plus 0.0. So s plus 0.1, s plus 0.01. Okay. Now we have to see the response. So we'll just add a scope. Then we'll have this. Because there are two signals we want to check. One is the reference and another is the response. So we add a mux. Mux will just concatenate these. We have this reference. We have this output. Let us see. Select this one. So if you see, this yellow one is the RAM signal and blue one is the response. Okay. For this compensated system. Now we were expecting that with respect to this uncompensated system, basically with this gain modified, we'll have less error in this compensated system. So we'll just compare that one. What we have, 7 has this system, delete it, then we have this one, and this one is simply 1. We'll just remove it, and we'll just simply short circuit this one. Disconnect this, and this is a reference, and this is the output of uncompensated system. This is transient improved, only transient improved. And this is transient and steady state improved. Okay, let us see. You can see on if it is improved or not. We want a legend. Can you find this one? Yeah. I hope this is visible. This one is the transient and steady state improved. So this blue one, if you see the error, between the yellow, which is a RAM signal, and the one system with compensator, that is lag compensator, is less compared to this ramp, and red one. Red one is only with the transient response improved. So we can verify that okay, this there is an increase in kV, and that is approximately this kV equal to 20 no? Or 10. So the value that was given in a specification, it was 20. Okay, I hope this is clear now. Do you have any doubt in these questions? Any concept related to this compensator design using root locus, or any simulation using MATLAB? Is there any difficulty? My voice is audible, no? Okay, then I think if you don't have any doubt, then we can conclude this session. Okay. So you all can leave. Thank you. We'll meet next week. This is recorded.